Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture 55 and in this lecture we will be looking into the signal processing side of it. That means once the output from the qubits are available to us onto the readout circuitry, then how do you actually read the signals and try to obtain best output will be discussed here. So, we will be looking into the multiplexing techniques which are based on FDMA, TDMA and SDMA. These are known as frequency division multiple access, time division multiple access and space division multiple access. So, these three things we will be looking after as far as this is concerned. Now, if you look at the multiplexing techniques which are available to us, as I discussed with you earlier, let us understand first of all what is the meaning of multiplexing in communication, right, to manage. So, multiplexing is not only a term which is prevalent in quantum design, but they are also available in a plethora of communication systems and otherwise as well. So, basically multiplexing is very important in large scale quantum systems, and they are primarily used to effectively manage the communication between the qubits and the control electronics, right. Now, as you all know that, and we have been telling it from quite a long time now, that in cryogenic electronics where your temperature is around 20 millikelvin, reducing the number of physical interconnects is crucial to minimize the heats. Why? Because larger the number of interconnects which is there on the system, more load will be there, more resistive load will be there, and therefore there will be large amount of heat which will be generated. Further, this adds to the system complexity as well, because when you have large number of interconnects on the same area, the signals tend to overlap over each other through the interconnects, right, and therefore there is a good amount of overlap of signals between two neighboring interconnects. There is large amount of electromagnetic interference which is happening. Why this is required? Because the bandwidth is limited in terms of carrying the signal, but if you want to carry larger number of signal, larger number of bits, we generally use these multiplication or multiplexing techniques. If you look at FDMA, which is frequency division multiple access, then it basically separates the signal which is assigned to each qubit by a unique frequency, right. And typically if you want to do an ideal readout circuitry where you do a parallel readout, we use FDMA. So, it is frequency division multiplexing multiple access. Now, if you look at this is the frequency division multiplex access, which is number 1, let us suppose, and as you can see here, these are the chunks of information which is there, 1, let us say 2, and then this is 3, and what is doing is in the same time, if I send a frequency say F1, F2 and F3, so there are 3 frequencies emanating from 3 effectively different qubits in the same time domain, I am able to multiplex in the frequency domain, saying that these are very unique frequencies attached to the signal, and therefore, I say F1, F2 and F3 are the 3 unique signals which is attached, and this is known as frequency division multiple access, right. And with respect to time, if you see, this is the domain, signal domain, and these are the sort of blocks of information which are associated with individual frequency. Now, if I can get the output of a readout circuitry, output of qubit through multiplexers, if we can get that corresponding to each qubit we have one frequency attached to it, then what I can do in the same time domain, I can send n number of frequency cycles through the same path. That is known as the frequency division multiple access. Now, let us look at the TDMA or the time division multiple access, which is this one. This is time division multiple access, and this primarily separates the control and readout signal in time domain, right. So, this is basically the division is in time domain. So, I have a common line which is being activated, but in the time domain they are getting access. So, let us suppose at time t1, this one is, so at time t1 you have one, so at time t1 you have one signal, time t2 you have another signal, time t3 you have another signal, time t4 you have another signal. It is something like this, that if you have in a classroom having multiple students, right, in a classroom you have students from different classes, let us suppose you have a room filled with classroom students from class 1 to class 5, and you want to leave them to the classroom. The one way of doing it is in time domain, you let them work out serially. All class 1 students will leave first, then class 2 and class 3 and then class 4 and finally 5. This is a serial method of shifting of data and they are unique in time domain. So, in T1, one set of people will move out, the T2, T3, T4, T5 people will wait till all T1 has moved out and so on and so forth. These are all techniques so that within the limited resources available to us, I may be able to effectively like sort of communicate between point A and point B. Let us look at SDMA, which is also referred to as a space division multiple access, and this is uses the physical routing to separate signal paths, and therefore it allows you to reuse the frequency and the timing signals, right, across different spatial blocks. So, if you have for example, in this case, for example, time is the time and space, time and frequency. In space domain, these are separated in a sense, right, and that is the reason. So, what happens, the whole idea of either FDMA, TDMA or SDMA is that if you can carry a large number of signals of varying frequency, then it is FDMA. Signals at each time interval T1, T2, we define this to be a TDMA, and at space and the space side, if you are able to multiplex it, we define that to be as an SDMA. Now, either they can be used individually, that means individually you can use either one of them or you can use a combination of them, right. So, you can use them individually at one go or you can use in hybrid combination, right. And typically thermally stable quantum processors are allowed when you do these hybrid combinations in a proper fashion, but you need to understand that while doing so you need to ensure that the information is not lost while you are doing the multiple access in a sense, right. They are not lost in while they are being processed either of these 3 multiple access region. Now, as I discussed with you, because if there are 2 qubits or 3 qubits, it does not matter, but if you scale up the qubits, that is where the advantage of quantum computing comes into picture or quantum communication comes into picture. When you scale up the number of bits, you require much smarter multiplexing architectures, right, so that you are able to carry the information very easily and you are able to process it with the minimum latency in a sense, right. So, those things you need to ensure as far as designing at such ultra low temperatures are concerned. Now, let us look at frequency division multiple access in a much more detailed manner. So, the key features are that, for example, that let us suppose these signals are having unique frequencies. I can use it by doing multiplexing by sending it here, though this one is just the repetition of the earlier slide. I wanted to show you that S0, S1, S2 and S3, let us suppose, belong to F1, F2, F3 and F4. Then by thermometer coding, let us say this is 1, let us say this is 1, 0, 0, 0, then this frequency appears at F out. Then similarly, if this is 0, 1, 0, 0, then F2 comes out. Similarly, if it is 0, 0, 1, 0, then F3 will come out, and if you do so on and so forth. So, when you do 0, 0, 0, maybe 1, then F4 will come out, right. So, you can do a frequency division. These are combined into single physical line called S in or S out, and they are achieved by assigning unique frequency to each qubit signal. So, if you for each qubit, there are 4 qubits for example here, for each 4 qubit signals, if we have a unique frequency attached, then we can surely say that I can actually achieve a frequency division multiple access. And therefore, finally what happens, the benefits are that you basically reduce from 4 line to a single line. Therefore, interconnect efficiencies are much better. They are highly efficient in terms of physical interconnects that I was pointing out. So, you basically reduce from 4 line to about 1 line, right. And so, initially you had, if there wouldn't have been any multiplexing, then there will be 4 line carrying 4 frequencies, right. So, this is F1, F2, F3 and F4. Now, you have a single line which carries all the frequencies by doing an FDMA. This works very well if the qubits operate at distinct resonant frequencies, and that is more so the case. You should therefore need to understand that when the number of qubits becomes relatively much larger, at that instant of time this FDMA is of great importance, and you need to ensure that individual bits which you are proposing, or there are a number of bits, these bits should have very unique or distinct resonant frequencies. If they are not, and there is a overlap frequency between two bits, qubits, then it won't work, right? And this is the limitation. Now let's look at the limitation of FDMA. Of course, you need to do precise filtering and frequency isolation, right? So this fidelity of frequency needs to be taken very carefully, that you are able to isolate all the frequencies corresponding to individual qubits in a proper manner, and this requires precise filtering in frequency domain, and therefore isolation of frequency also is required. You need to also ensure that when you are actually isolating the frequencies, you do not let the nearby frequencies in a sense talk to it in a manner such that the center frequency or the frequency which you are trying to detect is get lost by this interaction. And the hardware should be able to separate and decode this frequency multiplexing circuits. Now these hardware requirements are quite heavy, which itself is a power consuming hardware, and that is the reason that the to an extent, if not fully, the gain which you get out of FDMA may be slightly lost because of effective hardware which tries to separate and decode the frequency multiplexed signals. Then you need to also understand that these multiplex signals, when they are received at the receiver's end, they need to be demultiplexed, right? And you should able to retrieve back the values of the frequencies F1, F2, F3 and F4, right? So two things happen in this case, and the first thing is you at the signal generation end, you need to multiplex it. Once it goes through the interconnects and it reaches the receiver end, you need to do a demultiplexing and try to retrieve back the old frequencies in a sense. Similarly, the problem again is that these FDMA have a crosstalk or interference if the frequencies are too close to each other, which means that if the frequencies are relatively closer, you cannot separate the frequency from the main value. So let us say I have a frequency which is 10 say gigahertz and let us say 12 gigahertz, then there is not a problem. But if it is a 10 gigahertz, let us suppose center frequency and have 10.000 maybe 1 gigahertz, then they are relatively very close to each other. Then how do you actually separate these out properly without destroying is very important. Not only that, when you are actually transmitting data which has been extracted from the qubit, if the signal center frequencies are very close to each other, there might be a chance of crosstalk between the two signals, and therefore there will be a noisy signal will be generated. Now let's come to TDMA and time division multiplexing. Is that within one interval you send one side type of signal, in another interval you send another type of signal, and we have used the same concept as the previous case, and we try to find out the value here, and we use a thermometer encoder to generate this line. What we do is that we also use this extra line here, which is referred to as 2 for timing control. This is for timing control, right? This is for timing control, and this is the timing control capacitor, right? So this will be where you will be doing the controlling of the capacitor in the TDMA axis. Now again, the advantage here is that benefit is 4 to 3 lines, as 3 lines have been generated, and 3 lines. Why? Because you have C01 also coming into picture, then you have this select in and output line is there, and then you also have a selection signal. So there are 3 lines which are available in the output. It is relatively easier to implement than FDMA, and as you can see that it does not require any specific filtering of frequency. Now all the qubits can share one bus and sequential in time. So it goes 1 by 1 by 1 by 1. So this is T2, T1, T2, T3 and T4, right? And it goes in a sequential fashion. And therefore that brings us to the limitation of the model, that the limitation is that the signals are accessed only one at a time, right, and not in parallel. Now, and as a result, the latency slightly increases in the sense, and that is what is the second point, that performance is time sliced. However, they introducing latency. So the latency actually becomes larger in this case, because for example, for T4 to happen, you need to wait till T1, T2 and T3 all appear in the output side, right, and then you can get T4 in the output. Requires this. So this requires a fast and low power cryogenic switching hardware. So please keep in mind that the access which you are doing might be very efficient, but the hardware which you are using, which is very highly switching, can actually give you large amount of dynamic power, and therefore your thermal budgets might even fail even if you have a good amount of timing access or time division multiple access system available with you. SDMA is the space division multiple access, which is referred to as SDMA, and this relies on the spatial separation of signal path. So it's not frequency or time, but the physical space the signal is separated out. Now, so it effectively means that each qubit, right, is assigned a dedicated physical wire. So, I do not do a multiplexing, I do not want the output to move through a single sort of path, but what I do is I do not require a dedicated line for a single one, but there are dedicated line for individual qubits as such, right. And therefore, I can use what is known as a time and frequency reuse in space. I can use the same frequency signal or multiple frequency signal. If they are separated in space domain, I can reuse them to carry forward. So, if you have a bandwidth limited systems, SDMA works very fine, right, and it is used in many places in hybrid architecture, which consists of both FDMA and TDMA and FDMA. So, as I discussed with you just now, SDMA physically separates qubit access path, right, and therefore, there are unique wires or dedicated routing is available for you in SDMA. In hybrid configuration, SDMA allows reuse of time slots of frequency bands, as I discussed in the previous slides, and within even the spatial regions which you have, the reuse of time or frequency slots are available, and this allows parallelism without interference, right, and useful when operating on a qubit subarray. So, if you have a large number of subarrays of qubits, such type of space division multiple access gives you a much bigger advantage, not only in terms of efficiency, but also of frequency and time reuse across the network. Something which is disadvantage to it is basically the space requirement, physical space requirement, because you require individual wires to take care of individual qubits. Okay. So, we have already seen that what are the benefits of SDMA in quantum systems. There is a parallel access to different qubits without crosstalk. The probability of crosstalks are very low in when you do an SDMA system. They are compatible with FDMA and TDMA for building large multiple qubits arrays. They leverage space based isolation, right, and that is I have already discussed with you, and therefore, it reduces my bandwidth saturation and reduces signal overlap. Signal overlap is almost is gone, it is not there, and the bandwidth saturation does not take place because you are separating in the space domain, not in the frequency domain. So, I can use the same frequency or I can use the frequency at different space domain, and the same frequency can be used in different space domains. Similarly, the timing and synchronization circuits can be controlled independently, right. So, the timing and the synchronization circuitry, when you have localized space based qubits, this are controlled independently, right, and that is that sort of a benefit which SDMA has in a quantum system. Okay. So, just to recapitulate about the three techniques which we have just now learned, and we will go by the feature on the first column, and we have the three types of access on the second, third and the fourth column. So, the feature is resource separation. Resource separation in FDMA is by frequency, TDMA is by time, and SDMA is space. Space basically, when I say, I mean there is a wiring layout, or individual qubits will have individual wires associated with it to carry signals. In how does efficiency scale in case of FDMA? It gives you number of frequency carriers. So, multiple frequency carriers can be done F2, F1 to Fn, and in TDMA there are large number of control qubits available. In SDMA, I can use the space qubit across all the qubit blocks. Is parallel operation possible in FDMA? Yes, we can have multiple frequency generated. TDMA, no, because as I discussed with you, it is a sequential access, right, block by block the data will go, and in SDMA because of spatial isolation you can generate parallel operation, but the cost you pay for it is larger number of wiring layout, etc. Now, heat or wire load medium is wire load reduction. Reduction is much larger in case of in FDMA. In case of TDMA, it is relatively very high, and SDMA it is between low to medium sort of load is there, load reduction is there. Use cases in FDMA is used for reflectometry and RF readouts. All RF readouts use FDMA. TDMA is for clock control and signal sharing, and these are hybrid architectures, hybrids of what? TDMA and FDMA, correct. So, these are the application domain which is being formulated for SDMA and TDMA. So, let me quickly go to quantum computing qubit scaling, and let us look at the milestones achieved in quantum computing is sort of a historical background, and what are the physical qubits needed for scaling quantum computing. So, in the very early days was around 1990s and 2000, when initial quantum processors demonstrated only about 2 to 5 qubits. Anything more than that was not developed at that point of time, and it was more of a POC, proof of concept experiments, right. For example, quantum teleportation and simple gates, and basic gates and its realization was done to showcase in the early days. However, using first 2 qubit gates using nuclear magnetic resonance quantum computing was done in 1998, and limited scalability due to high decoherence and lack of error correction was done also in the around the same time. Then in 2010s we had a specialized platform, and that offered hundreds of qubits, though not fully programmable or error corrected, which means that though those qubits were there, but you cannot program from an external source to change the qubit, right. You cannot change the qubit to a larger extent, and you cannot control it, you cannot do an error correction, there was no feedback system available to you. Okay. Most systems still lack gate level fidelity, and if you want to do a good amount of quantum computing, you require gate level fidelity in a sense, and your coherence time, connectivity and control accuracy was not relatively good, but was going on improving as we moved across the 2010 decade. Now, if you look at the quantum supremacy milestone which was set in 2019, the Google Sycamore processor was having 53 qubits, superconducting qubits, and executed a task in 200 seconds that would take classical computers about 10,000 years. So, maybe for the first time you are seeing a number where you see a drastic improvement in the convergence of algorithms, and because of very fast nature of qubits and its parallelism, you are able to solve a task which in very small time, in this case about 200 seconds, that would actually take a classical computer 10,000 years, right. And then for a specific task, it was shown that 2019-20 that for a specific task somehow the quantum computers were much better as compared to classical computers. However, as I discussed with you, there is a problem of scalability in quantum computers, that you cannot scale it beyond a particular point, and you also have limitation in terms of error gates and algorithm applicability, how many algorithms you can applicable, right. So, let us look at the present capabilities now. 2025, of course, IBM operates with 127 to 133 qubit physical qubits known as Eagle processor, and it targets about 1121 qubit Condor chip. They are trying to go ahead with that. This is IBM's quantum mission. IonQ, an ion trap system with 30 to 40 high fidelity qubits available, modular, they are very modular in scaling types of roadmaps. And then Quantum achieved 32 to 34 error free operation using trap-time architecture. Trap-time architecture, these are various architectures which are available for the qubit, superconducting, trap-time and transbond based and so on and so forth. So, there is a push within the academia group and the industry towards 1000 plus qubits by 2025-26. Please understand this number is generally a rough candidate where everybody wants to achieve it. A good idea or a good beginning has been made already in India, as you must be aware of, because of National Quantum Mission in quantum computing and quantum communication and materials leading to quantum and so on and so forth. There are a large number of academic groups across India working in the domain of quantum computing with the industry partner. Typically, they are focusing on error correction, multiple engagement and system stability for meaningful applications. Okay, so I will stop here and we will go for the next set of systems in the next class. What we have learned till this whole discussion and recapitulation was give you an idea about the various types of multiplexing which is available in order to ensure that the most information is reached in the output world with maximum throughput and least latency. But we saw what is the relative advantages and disadvantages of FDMA, TDMA and SDMA. We also looked into the various application domain of all these three, and we came to know that which one is the best. So, SDMA is a hybrid sort of connectivity, whereas TDMA and FDMA are purely on the frequency hopping, frequency division and time division. Finally, we looked into the how the quantum world has moved forward in terms of from where we were initially and now what is the current state of the art which is available to us. We actually looked into that. In our next class, we will continue moving forward to the development, and then we will end our discussion on how to design the quantum gates at cryogenic temperature. I hope you enjoyed the lecture. Thank you.